told you what random variables and distribution functions are, because you plotted this histogram and you saw that, like, okay, so I have this random thing, I don't know what the return is going to be this year, the market return for S&P 500. I can think about that as a random variable. And we constructed this distribution function from the data. Okay, but I want to do a little bit, I want to put that in a little bit more of a formalism. So we're going to have about 15 minutes of formalisms where I'm going to really define the random variable, the sample space it's acting on, what can I ask for probabilities about. Then we're going to do a bit of an exercise to really like drive home for you what are probabilities, what are distribution functions, how do I go back and forth between the two. Then I'll go back to formalisms a little bit, and I want to talk about summary statistics, but whereas I think you're all familiar with taking Excel and doing an average or a standard deviation on data, I want to make sure we know the relationship of how do I do that when I give you the distribution function. So that another way we can think about it is I eliminate the data step and I say, you know, there's some data, I've figured out what the right distribution function is, you trust me on that, and then we move forward. Okay? So I also want to make sure you can do summary statistics from the distribution function. And then we'll end with another exercise. So I kind of got it split up between some formalism stuff and some exercise active stuff. Okay, so let's start with some formalisms. I want us all to have the same vocabulary. So that's one thing that I'm doing here, is making sure we have some common vocabulary. And I want to talk about sample space. First, sample space. So sample space is a set of all outcomes of a random experiment. So in our game on Monday, you didn't know what return was going to come up. That was our random experiment. Your sample space was all the different market returns you had seen since 1928. Okay, so that's one. But it's not that a sample space has to be numbers. I could think about flipping a coin. I don't know if that coin's going to come up heads or tails. Sample space is heads or tails. Or if I flip two coins, it's probably heads, tails, heads, heads, tails, tails, depending on whether or not I want the order of did the first coin come up heads, the second coin come up tails, or vice versa. I can think about a horse race. If I have 3 horses entered, so my sample space is A comes in first, B comes in second, C comes in third, B comes in first, A comes in second, C comes in third, all the different combinations of that. Or I can think about the time until the web page loads, and now we've got something a little bit different because this is probably not something I enumerate like horse A, horse B, horse C. This is maybe it takes 30 seconds for the web page to load, maybe it takes 44.3322. So there's really a continuum. It's really like it could take any time probably greater than 0 for this web page to load. The random variable, and I'm usually denoting, when you see a capital letter in this class, it's common to denote random variables with capital letters. So if you see a capital letter, that's generally representing some experiment and you don't know what the value is. And it maps the sample space to the real numbers. So sometimes it's really easy. In this stock returns game, the X would just be exactly what stock return came up. If it denotes the coin flip outcome, I just want to make it clear that when I say sample space for coin flip, I got a head or a tail. But when I talk about the associated random variable, I'm going to assign it a number value. Whenever I talk about a random variable, I want a number value. So even though the coin was head or tail, the random variable is like 0 or 1. Okay, so I'm always going to go from something that's not a number to a number. Or for example, in this sample space with 2 coins flipped, maybe I'm keeping track of 4 different things. The head, head, the tail, tail, the head, tail, the tail, head. But maybe the random variable is the number of heads. So I actually only have 3 things, 0, 1, or 2. Okay, so it could be that the random variable is consolidating some things that happen in the sample space. Or for example, if I just want the placement of horse C, the random variable just needs to keep track of 1, 2, or 3. And this would be the same. If my sample space is time until the web page loads and it is just some positive number, probably in, I don't know, seconds, then my waiting time would just be exactly the elements of the sample space. And you can see that there's a distinction. So some of these things are discrete. When I say discrete, what I mean is we can enumerate every possible outcome. The coin flip is head or tails. That's it. The waiting time here is continuous. If I think about the time until the web page loads, it's a time. It could basically be anything more than 0. Maybe it's got a lot of decimal places after it, 0.923334, 6, 7, 8, 9. So it's not like I can enumerate every single possible thing. It's like I need to think about intervals or something like that. So I'm just making the distinction between this is discrete and this is continuous. And we're going to focus right now on discrete, so for the next week we'll focus on discrete. But there's some motivation for continuous actually from last class. Because when I asked you, are you happy with the way I sample returns? Well, probably our data set didn't include every possible return the market can ever give. We agreed that like that list of data was probably not equivalent to the market can only return exactly those values. We probably actually wanted to put something continuous on that. Okay. So that's the motivation for why we're going to jump to continuous random variables in, I said about a week or so. But today is all discrete. And differences understood? That's good. And here's just a graphical representation, so I'm reminding you if I have a sample space, it may or may not be a number, but when I take the random variable, I got a clear mapping, the head goes to a 0, or the head goes to a 1. Okay, but there's always a one-to-one thing. If I say x is 1, I know it was a tail. If I say it was a tail, I know x was 0, or whichever to make sure they're in agreement. Okay, so the other language is events. So when I say event, it means I've got a random experiment in the background, and I've got a sample space. An event is anything I can ask probabilities about. So let's think of an experiment where I roll a die. If I roll a die, I could get 1, 2, 3, 4, 5, or 6. And I'm going to use that simple example throughout quite a bit of this class just because it's a very easy illustration, and I think in our heads we all know what it means to roll a die. So I can ask for the probability of any element in it. I can ask for the probability I get a 1. I can ask for the probability the die lands 3. But I can also ask for more involved things. I can ask for the probability I get an even. So I can ask for the probability I get a 2, 4, or a 6. So when I say event, I mean any combination of things in the sample space. And in particular, it means that I'm allowed to ask probabilities about it. If I tell you I'm rolling a die, my sample space is 1 through 6, and you ask me what's the probability it's going to rain tomorrow, that really has nothing to do with what I told you. So the event is my way of formalizing, this is everything we know something about that we can calculate probabilities for. Okay, so just some more event examples just to kind of get our feet wet a little bit more. So let's say I'm tossing 2 die. If I toss 2 die, I've got 36 points in the sample space. I've enumerated it in a table here. I get a 1 through 6 or a 1 through 6. And so it's a 6 by 6 table. There's 36 possibilities. And maybe the event I'm interested in is the sum of the dice equals 7. So if you're a craps player, which I'm not, but I understand in craps 7 is pretty important. So maybe when the probability of 7 comes up. So if I want to think about the probability of 7 comes up, well, it's really this diagonal. So 6 plus 1 is 7, 5 plus 2 is 7, 4 plus 3 is 7. It's this diagonal here in the sample space. That gives me 6 possible points. So my event is these 6 possible points that correspond to the sum beads. Okay, another thing is if I'm thinking about something with a continuous sample space, I said we wouldn't really be talking about it in this class, but I guess I will just a little bit more. I have a Kindle, I'm very attached to my Kindle. I don't want it to fail, so I want to think about what's the time until my Kindle fails. Well, the sample space is the positive real line, so it could fail any number of months from today, or any number of days from today. And my event, if I want to make sure it lasts 3 years, and I'm talking about days, so this is the event that my Kindle's going to last for 3 more years. Okay, or maybe I could think about weights of newborn children. Is the child sort of normal weight or abnormal? So this event is corresponding to the child's born less than 6 pounds or more than 9 pounds, which would be an abnormal. Okay, so in each case I had an event, I had a sample space in the background, I had some combination of events in the sample space. And just like we could graphically think about going from sample space to real line, for an event, you can think about having a subset of things in your sample space that you're interested in, and that should map to some interval, or some values on the real line. Maybe they're continuous, oops, maybe they're not. far. We have sample space, that defines your random variable, defines the values the random variable can take on, and events. The sample space defines events, what can I ask probabilities about, and what values might that random variable. How do we define the probability? So that's the distribution function. So the distribution function is when you did that histogram plot, that was the cumulative percentages that we plotted. That was that red line that was increasing as the order. So whenever I give you a random variable, it's defined by its distribution function. And if you know the distribution function, you know everything about that random variable. So I said you'd be seeing a lot of die rolls. Here's a die roll again. So if I have a die roll, there's two things I can talk about. One is the probability mass function. So the mass function is the probability assigned to each particular outcome. So that's just 1/6. The die can be 1, 2, 3, 4, 5, 6. It's all equal probability. The distribution function is thinking about that histogram. That's the cumulative. That's the sums. So if it can be 1, 2, 3, 4, 5, or 6, and they're all equal probabilities, if I think about the distribution function, I'm thinking about the probability less than or equal to 1 is a 6. Probably it's less than or equal to 2 is 2/6. Less than or equal to 3 is 3/6. So I'm just summing up this probability mass function. And you can see the correspondence from here to here. And probability should sum to 1, so your distribution function here should always end at 1. And this is an example where everything is equally likely. It's not that everything has to be a 6. Maybe in other examples, some things are a 6, some things are 4/6. These could vary. And one point I want to make is it's completely equivalent to specify either. Sometimes I'll give you a distribution function, sometimes I'll give you a mass function. If you know one, then you can get to the other. How do I calculate probabilities? I can add stuff. So I think we've already kind of been doing that, but let me just make it explicit. So if I'm talking about the outcome of a die roll, and I want the probability that the die roll equals or exceeds 2, we've actually already been doing this, but now let me say it formally. So the probability I'm greater than or equal to 2, well, it's the probability of the die, I'm interested in the event, that I get a 2, 3, 4, 5, or 6. And so I add the probability of each particular point in that event, and I get 5, 6. If I want the probability that the die is odd or a prime number, I'm interested in the event that I get a 1, 3, or 5. 2 is also a prime number. So I'm adding 1, 3, 4, 5, I get 4, 6. Okay, so calculating probabilities, you're adding. Okay, so that's my a little bit of formalism. And now I have a bit of an exercise to make sure that it's clear in your head this idea of getting at the distribution function and getting at the mass function, and how do I maybe use the distribution function to make a decision. So my exercise, it's a capacity provisioning, and you are consulting for the famous news organization Trojan Real Time. TRT has been having problems with the response time for their online content, that is how long it's taking to load their web pages. And your first step is to double check their capacity provision. So what I mean is, do they have enough web servers? Let's assume that each of their web servers can handle 1,000 requests per second, and that the cost per server is $500. And I put a little caveat, this is a simplification. I'm not counting caching, I'm not counting something like Akamai does. I'm just saying, let's kind of take a simplification. One web server gives me 1,000 requests per second. And I posted an Excel file to the Blackboard, and this is web server example. And that provides a snapshot of the traffic that TRT is experiencing. So what you can think about is, here's the file I posted to Blackboard. And you can think about it, what I've done is, for different seconds, I've taken an observation to see how many requests are coming in that second. And so here's 1 second, I'm getting 17,781 requests. Another second, I'm getting 11,624 requests. Another second, I'm getting 13,898 requests. Okay. So this is giving you a sample of what I'm seeing in terms of how many requests are arriving for TRT every time. Now you're thinking about, how many servers do I need? And if you purchase in servers, we're going to assume that the number of requests that can be handled at any given second is 1,000 in. Everything else is lost. So I'm not going to somehow queue up the requests and serve them later. I either serve them in that second or I don't. And the objective here is to minimize costs, subject to ensuring the probability of request cancellation is less than 1%. Okay, so let's think a little bit about what that means in terms of this Excel file and our random variables and our distribution function and the formalisms. So we've got a random variable that's x, and it's representing the number of requests that arrive in a given second. So x here is a discrete random variable. You know, it's not 1.5 requests that are going to arrive, it's 1 or 2 requests that are going to arrive. So it's basically some kind of positive feature. And if I want to minimize cost, I want to find n, this is the number of web servers I need to purchase, such that the probability that the number of requests that arrive in a second is greater than 1,000 times n, this is my capacity, should be less than 1%. Or an equivalent way to write this is the number of requests that arrive in a second. This should be less than or equal to the frequency with which it's less than or equal to 1,000 n, that's my capacity, had better be greater than or equal to 99%. So at least 99% of the time, I'd better have enough capacity to satisfy all the requests. So this guy here is exactly the distribution function. So if I have the distribution function of x, I can exactly figure out this guy, which tells me how many web servers are getting. So n I get to decide on, that's like my decision variable. X I don't know, this is this random thing, and I want to estimate its distribution. And I've set up a little bit of structure for us to get started, because another purpose here is I want to make sure we can all go between CDFs and PDFs. So in the first step, what I want you to do is I want you to construct from data both the CDF and the PDF. Sorry, probability mass function. So the probability mass function here is I'm just looking at basically the frequency of times that I see each of these number of requests arriving. And over here, I'm looking at the cumulative. And once I find that cumulative, then I'm going to go over here and I'm going to translate to, if this is the number of servers I purchase, this is the probability that I'll be able to satisfy all these requests. Does that make sense? And I've given you a couple hints here in step 1 and step 2. Okay, so if the question makes sense, then let's take kind of the next 10 minutes. So please feel free to talk to each other, work in groups. I want you to start by constructing this mass function in this CDF. And step 1 really does get you started pretty exactly. And I'm going to float around if you want, if you have questions or. X is the number of requests in 1 second. Yes. So X, I'm looking at the number of requests that arrive in 1 second. And any of you that don't have your name tags, if you can start bringing name tags, that will be great for me. So if you have them and they're not out, please put them out. You just didn't bring it next time. And yours is very creative. This is even harder.
Brian, where's the gold tag?
the value of the next which is X. That top.
Oh, the big.
Yeah, okay.
Over here, so it started out, this one just equals there. Very easy. Actually, I think it's easier if I put this PDF properly.
Until I guess I do it. That's the tool I'm gonna have to have. It's not the way down. If I find it, so if I study it today, will it be in here, right here? Okay. Is it oh, I'm sorry. Right here. Okay, raw one. Okay. Oh, session one. Oh, this one. Oh, the web example? That's all I have to let me see. Maybe yeah. Yes, I did. Let me see if I can try to get an alternative until I can. Office, open office. Didn't we try to use Excel so you don't have to try to also. Google spreadsheet? Oh, okay. How about open office? Can we try that one? Never before?
And now I'm thinking, when I send this together,
Oh, okay. Oh, okay. Oh, okay. Your family out in New York? Oh, I see.
He's usually my go-to guy.
So here, all I want you to do is I want you to count the number of times this is appearing in your data set.
Okay, and so what do you mean by this is appearing? Like, I only have
79 times there was a second and nobody came.
Okay.
And now I'm gonna have you count the number of times there's exactly one person. And there are gonna be a lot of zeros, so actually you do know what you're doing. It's perfect.
Okay.
I think you're worried because there's a lot of zeros.
That's freaked me out every
Everybody
time I
is-
do it. It's good.
What I'm trying to give you here is, these are pretty large numbers. And I've given you some kind of, 3,600 seems like a lot, but it's a lot less than 92%. So why would I expect that I've seen every possible thing that can occur? I have to.
True. Yeah.
So just interpret it that, exactly. So you will get a lot of zeros, and don't let that worry you. Yes, P is exactly the number of times I've seen this occur, and the F is the cumulative if you think about the histogram. So this is the number of times I've seen something less than or equal to that number occur. Yes, so it's basically summing everything less than that 1,000. Or Bora? Yes, okay, so that.
There's like, if it's less than like 1,000.
Yes, so you guys have first part, you can just look at your CDF and look at the first time you get 99%.
Oh, so we don't have to like necessarily fill anything in here. Just like,
No.
this is 99.
Yeah.
Then divided by 1,000, and that's
Actually, hold that thought for just not quite. So I wanted, if you have one server, what's the amount of demand you can satisfy? So I'm gonna give you the table. Actually, hold that thought for 1 second, because I think we're gonna say it to everybody, and I think it's the same question, so just ask me what you're talking about. Actually, let me say it to everybody now, and I just posted my slide. Is that okay? Sorry, Okay, so I've just posted my slide to Blackboard, and my sense is that most of you guys are getting the PMF and CDF construction, but a few of you are thinking about how do I do this last number of servers. So let's just make sure first that we all have the difference between the mass function and the distribution function. So here in this probability, I'm just asking for what's the frequency of times in the data set you see a particular number. And it's a normalized frequency because I want it to be between 0 and 1. So if you look at 0, what this is telling me when I do this count if function, and this count if is exactly what you're seeing here, is I'm counting the number of times in the data set that 0 appears. And I'm dividing it by 3,600 because I have 3,600 observations. Now, I kind of overheard, and when I float around, it helps me to kind of get a radar screen on where you are and what you're talking about. So I kind of heard several people being a little disconcerted because there's a lot of zeros in this data set. So what am I thinking about when I'm thinking about these zeros? Well, you know, the number of requests that can arrive, these magnitudes are sort of, in general, more than 10,000. But I only have 3,600 observations. So if I'm thinking that, you know, the minimum I have here is 0, the maximum I have is 26,840, there is no way I've possibly seen every possible number of requests that can arrive in a second, right? I've just seen a sample of what can happen. So I would actually expect when I try to count these frequencies, and I'm thinking that, you know, the number of requests that can arrive in a second, it can be anywhere between 0 and this maximum. It's not like I think that If 0 is the maximum, the minimum that appears in the data set, and 26,840 is the maximum, that there's some special numbers that it could never be 3,000 requests in a second, right? Okay, so that's kind of why you're seeing a lot of zeros. Is that making sense? Okay, so here I'm just giving, again, this is normalized frequencies of what's happening in the data set, and the F is like the cumulatives. That's like when we did the histogram, that is the red line that was kind of increasing. And so this is counting the probability I'm less than or equal to a number. So here, if I look at F3, this is just E11. This is the probability I see less than or equal to 0 requests. I'm never going to see a negative request, so it's exactly equal to that probability. If I go down, and maybe I should make this a little bit larger. If I go down to F12, this is the probability I see less than or equal to 1 request. So this is the probability I see 1 request, plus the probability I see 0 requests, which is why I'm doing E12 plus F11. And now you want to copy down. So this is what I mean by it's completely equivalent to have the distribution function or the probability mass function. Because if I have the mass function, I'm going to do sums to get the distribution function. If I have the distribution function, I'm going to be subtracting to get the mass function. Is this good that everybody's good on columns E and F? Okay, so then now let's go to this last column, and this is kind of the crux of the question, which is how do I use this distribution function to make a decision? And what I want to do is I want to make sure that I can satisfy 99% of my requests. And Paige, I think you asked me something about do I have to use the VLOOKUP function? Well, I don't, right? To satisfy 99% of my requests, I just need to look at this distribution function, and I need to scroll down until it gets to 99%. And when it gets to 99%, which is somewhere way down here, let's pretend that was 99%. I would look over here and would see what the x value is. So this is a little bit labor intensive to do. Oh, here we go. So I'm scrolling down, I get some 99%. Okay, so it looks like, okay, so this is 99%. So over here I can satisfy sort of around 21,000 requests. And remember, each server can satisfy, it was 1,000 requests, so it's looking like I need like 22 servers. Why did I suggest that you do the VLOOKUP function? Because that was a little bit manual. So another way we could think about this is, in column H, I have just the number of servers, right? So column H is giving me the number of servers. And in column I, what I'm going to do is I'm going to look at what's the frequency of times, what's the probability that that number of servers will satisfy all the demand that comes in that second. So if I have one server, I have capability to handle 1,000 requests. So as long as 1,000 or less requests come in, I'm in good shape. I have enough capacity. So what I'm doing over here is I want to do a VLOOKUP. And the VLOOKUP is, I'm going to do H11 times 1,000. That's my first argument, because the number of servers times 1,000 is giving me the number of requests I can handle. And now I want to highlight, so D11 to F. So my relevant table here is between D and F. And what I'm doing is I'm looking here, I'm going to look for the x value that's 1,000, and then I'm going to come over here and find the f of x value, because that's going to tell me the percentage of times that I'm able to, that I have the capacity to handle that number of requests coming in. Okay, so then that's something I can copy down, and actually I made a mistake here because I need dollar signs. So if you downloaded the sheet I posted, I forgot to put dollar signs. So let's redo that. Shoot. That's not what I meant to do. Okay, so I need the dollar signs. There's the dollar signs. And now I'm going to copy down. And so what this is telling me with one server, I can handle 1,000 requests. This is giving me the probability that 1,000 or less requests come in per second. And so what I'm doing there, we can just verify, 1,000 or less requests come in per second. I'm going to X. I'm finding where X equals 1,000. Oh boy, this is gonna take a minute. Okay, there we go. I'm finding where X equals 1,000. And I'm saying, oh, that's 0.036389. Okay. And then I'm copying down. And so now what I can do with my table is I can say, oh, okay, so what's the first time that I can satisfy 99% of the requests coming in? So the first time I can satisfy 99% of the requests is with 22 servers. And I posted my spreadsheet on Blackboard, so if I went over the exact syntax for that VLOOKUP command, it's on my spreadsheet posted on Blackboard, minus the fact that I forgot to put dollar signs, the F4. And the reason I put it in the table is for answering the question, we just needed to do this 99%, right? But if you're thinking about this, you might want to do some trade-offs for yourself, right? If you want to satisfy 99% of your demand, you need 22 servers. But you know, the servers are costly, so maybe you only want to satisfy like 90% of your demand, in which case you only need 17 servers. So you can kind of think of doing a cost trade-off for yourself between the number of servers you need and how much of your demand you're going to be able to satisfy. Is that good? Okay, so main point of this example that you should be getting out of it is you should be able to be comfortable going back and forth between probability mass function and cumulative distribution function, in computational stuff. And you should be comfortable with what this distribution function means. Okay, so then if I think about my agenda for today, I said there's some formalism, then there's a break for an exercise, and then there's a little bit of formalism again, and we'll do another exercise to end class. Okay? And I will go for formalism again, which is I want to define what these summary statistics are for discrete random variables. So I want to start with a probability mass function or a distribution function, and I want to calculate expectations and variances. And I'm going to do this in the context of a die roll because I think, like I said, I think it's kind of simple. We all know you toss a die, it comes up 1, 2, 3, 4, 5, 6. It's got probability 1/6 of each of these numbers. So I'll do the calculations with that, just as illustration. So as illustration for what an expectation is, if I want the mean of this die roll, it is all the values the die can take on, weighted by the probability it takes on each of these values. So it's 1 times a 6, plus 2 times a 6, plus 3 times a 6, etc. It equals 3.5. Notice that as a weighted average, the die will not actually assume the value 3.5, but it is an average of all the values it can take on. You want to see a general formula for it. This is a summation, so this says sum, and this is telling you to sum over all possible values x that this random variable can take on. So if you like the formalism, you have it. If you prefer to think in your head, I have a weighted average, and I'm weighting the values the random variable can take on with the probabilities, that's what you're doing. Now, there's no reason I have to think about this as expected value of x. Sometimes I want some function of this random variable. So maybe I want like expected value of x squared. And I don't have a strong motivation for x. Maybe a stronger motivation is you see demand and you're actually interested in the revenue that that demand brings you. But the data you have is on your demand. So you want to go from demand to an expected demand to an expected revenue. So how do I do something like this? Well, if I want like the expected value of x squared, it's so 1 squared, all the values the die can take on, and I'm squaring them because that's the function, and I'm weighting them by the probability it takes on those values. So it's again a weighted average, it's just that I square because I said square. And that would be the same for any function. So if it wasn't squared, if it was something else, I would be looking at the function of the value the random variable takes on times the probability. relationship between expectation and probability that's just kind of nice to see. And I can think about an indicator of whether or not an event occurs. So let me add my example here. Here we go. So let's say I have some event A, and if the event a die lands on a value less than or equal to 3, and I want the expected value of the indicator that is 1 if the die lands less than or equal to 3, and 0 otherwise. So if I ask you for the expected value of this indicator, just telling me whether or not this occurred, well, it should be 1 times, I'm going to weight it with the probability of that event occurring, plus it's going to be 0 if it doesn't occur, and I'm going to weight it by the probability the event doesn't occur. So I'm just interested actually in the probability of the event occurrence. So this is exactly asking for the probability that the event A occurs. And in this case, for this die roll, it's a half. If you like that, I just made a little connection between expectation and probability. Good. If you didn't like it, that's a little bit of an aside. Just properties of this expectation. If in this class, whenever you see capital letters, you think of random variable. This is something you don't know. This is like the stock market return next year. If you see lowercase, you can think of this as some number that you do know. So A and B are like 2 and 3. So if I have some linear function of this random variable, I can just take out the constants it adds. So this is like A expected value of X.
Is the A with the line over it the complement of A?
Yes. Yes, which I didn't actually define. Thank you. So this is meant to be everything that's not in that event A, but can still happen in the sample space. Okay, we can also talk about variance. So what is variance? Variance is actually a random variable, or it's defined through a random variable. So X is this die roll, and let's think of mu. So it's common to represent the mean as a mu. So X minus mu here. This is a distance. You can think about it, if the random variable is often taking values near its mean, this is going to be small. Taking values farther away, it's going to be large. So in our stock market example on Monday, those returns were all over the place, right? The mean was like 11%, but you saw returns all the way down to like negative 30% and all the way up to like 30%. So you could imagine that that distance might be large sometimes. And the variance is just the expected value of sort of how far away is that random variable from its mean. It measures a spread. And there's an equivalence in the formula. So it's equivalently expected value of X squared minus the mean squared. I'm going to let you trust me on that, but if you want to see the derivation, I'm posting notes after the class so you can sort of look at it. So if we want to calculate the variance in the die example, what am I going to do? Oops. What I'm going to do is I'm going to go back here. I'm going to say, okay, I know the variance of X. This is expected value of X squared minus this squared. So what does that mean? We calculated the expected value of X squared, that is 15.167 minus, here this tells me to square the mean, so this is 3.5 squared. And if you sort of do that algebra, you're going to get 2.917. And I said that was equivalent to this. So I think it's just nice when I say something's equivalent, you don't have to trust me. We can like verify it for ourselves. So if I wanted you to do this, so what is this? This is also what I'm calling expectation of a function. X is a die. It can take on 1, 2, 3, 4, 5, or 6. So what happens if it takes on 1? I'm asking you to do 1 minus the mean. We calculated the mean is 3.5. And to square it, and what's the probability the die takes on a 1? 6. Okay, so there's 1. Okay, it could also be 2. So 2 minus 3.5 squared times a 6. So I'm going to go through all the possible values that this die can assume, and I'm going to weight it by the probability it takes on those values. And if you do out that algebra, you're going to get 2.917. So it's completely equivalent to calculate it either way. It's whichever one you prefer. I usually find this shortcut easier. But does that make sense? We're going to do it in a second, so. Okay, and I also want to make the point that the variance is not linear. So I said if I take the expected value of AX plus B, you have A times expected value of X plus B. With the variance, you know, if I add a constant, you're not adding any variability. So if you have a random variable, you add a constant, that doesn't add anything to your variability, which is why the B drops out. The A is a constant multiplying this random variable, and you can sort of see there's a squared there, so it's coming out and being squared. That I have the handwritten derivation, but I'm not going to do it. You are going to look at my notes after class. Is that fine? Fair? Okay, standard deviation is square root of variance. And I think a nice measure, so we could calculate it in the die example. I think a nice measure is actually coefficient of variation, because if you think about standard deviation, I don't necessarily know what it means. Is it high? Is it not high? But if I compare it to the mean, that's the coefficient of variation. So I'm looking at the standard deviation compared to the mean. So here, 1.7, that would actually be really small if the mean of the random variable, your average is around 100. But if the average is 3.5, maybe it's not so small. So this kind of gives you a way to look at the variability in any random variable that's kind of normalized across all situations. So in this example, it's 1.7 is our standard deviation, divided by our mean. Coefficient of variation is about 0.5. Okay, so measures of variability. Oh, and I have interpretation. So this means variations around the mean can be roughly half as large as the mean. So if I know my mean is 3.5, this means this die is quite often likely to be rolled either 3.5 divided by 2, so 1.7 lower or 1.7. How about median? Median is a 50%. So median is 50% of the time the die is less than or equal to 3. Right? Probably the die is less than or equal to 3 is 50%. Actually, let's go back for a second. Okay, so if I look at this die, right, what I've done here is I've listed the values the random variable can assume. It can be 1, 2, 3, 4, 5, or 6. And this is our CDF, which we're familiar with, right? So the probability I'm less than or equal to 1 is a 6. The probability I'm less than or equal to 2 is 2, 6. Probability I'm less than or equal to 3 is 3, 6, so a half. Good. Okay, so if I want the median, I want the probability, I want to find the CDF that gives me 50%. So here we go, is 50%. And what does that correspond to in X? That's 3. So 3 is a median here. But what about the probability that the die is less than or equal to 3.5? That'd be exactly the same, right? Probably the die is less than or equal to 3.5 is also 50%. So any of these values between 3 and 4 you can think of as a median because the probability the die lands less than them is 50%. There's nothing special about the median of 50%. Suppose I asked you for some kind of quantile. So a common one would be like the 25% quantile. So what is X such that 25% of the time I roll a number less than X? Yeah, so 1. Why did you say that? I said I want to know a number so that 25% of the time I roll a number less than that. So 1 here, so 1, 6 is 0.167. So the probability I roll a number 1 or less is 0.167. The probability I roll a number 2 or less is 0.33. 0.25 is in between these two. So 2 is too much, it's gonna give me something more than 25%. 1 is 0.167, and anything in between the 1 or 2 is gonna work. Okay. So I told you I tried to split up the class into sort of some formalisms and some exercises, so you guys have been very good for coming along with the formalisms for me. Let's now translate those formalisms into some of the things we're doing with the stock market. So I actually have this in 2. We'll do something with the stock market, and then we'll do an exercise for you to do without me. But this one we're going to do together. So let's think back to Monday's class, and I posted this investing example. And what I want to do here is I want to take everything that I've just kind of formalized, and I want to do it with Excel so that there's a translation between what I said on the slides and what I sort of formalized and what that means in terms of what you actually do to make the computation. Okay, my computer froze for just a second, so there we go. Okay, so this is what I posted. So this is CDF investing example. And what it is if you look at the first worksheet, this is just the returns that you saw last time. So this is your S&P 500. Now if I go over here and I look at the CDF, so what have I done? I've just done this for you. This is basically what you did in the first exercise. Not exactly, but similar. So I sorted the dividends. So this is everything, all the possible S&P 500 returns we saw, sorted from smallest to largest. And if you think about the game we played, I said every one is equally likely to occur. So there were 88 of them, so I'm just saying for the probability mass function, each of those values has 1/88 probability of occurrence. And then over here I made this into a distribution function. So this is saying, so this is now summing this probability mass function. Good? Okay. So now what I want to do is I want to use the formula we just learned, but I want to calculate these summary statistics like mean and median and standard deviation from my distribution function and my probability mass function rather than calculating it from the data like we did before. Just to make sure we see the equivalence. So let's do the mean. If I give you the probability mass function, how do I calculate a mean? So I'm going to say equals, and I thought maybe it would make this a little bigger. So I'm going to say equals, and that should be a sum product, and it should be a sum product of the values your random variable can assume, and the probability that it assumes each of those values. So when you do that, you should get something like 0.11412. And you can go back to yesterday's class, and I think a lot of you did the summary statistics on the returns, and you can see, oh yeah, okay, I got the average of 11.41%, 11.4%. So these are the same. Okay, so nothing surprising there. How about the median? So how I'm going to calculate the median? Well, this is like in our web server example, and I needed to know how many web servers. So this is, median is basically looking for, except now it's 50%, not 99%. So I want to find the CDF value that is 50%. So I'm going to go down here, I'm going to find the CDF value that's 50%. And what does that correspond to? It corresponds to a return of 13.52%. So this is saying that 50% of the time, if I do a random selection on this data set, I'm going to come back with a return that is 13.52% or less. Good? Okay, so I'm going to calculate this median, and I'm going to do 0.1352. Oops. I guess I have the percent in there, so. Okay. Did anybody use the median function in class on Monday? What did you get? In fact, you can look at my data and,
.87.
so we didn't get exactly the same thing. early definition of the median. Or almost. The median can actually be anything that gives me something between, it can be anything between 13.52 and 14.22. Agreed? Because if I tell you 14%, 15% of the time, 50% of the time in that data set, I see something less than 14%. So technically, 14% is also a median. One of the things we're running into in the median is not, so what is Excel doing? So let's take an average. Let's take an average of this 13.52 plus 14.22 divided by 2. So that's 13.87. So Excel is just returning, because there's a little bit of this non-uniqueness issue, it's returning the number that's like right in between that 50% and the thing that's going to give you something a little bit more than 50%. Okay, so what if I wanted to ask you for standard deviation? Well, if I want to calculate it myself, probably the easiest way is to use this formula that I've got, well, the expected value of r squared minus the mean squared and then take a square root of that. So let's do expected value of r squared on the way to do that. So if I want the mean of r squared, over here, if you'll notice in column A, I gave you squareds. So I want the sum product of, here I've got this squared function, it's the squared function of the returns. And then for each of the values those returns can take on, I've got the probabilities. So I'm doing a sum product of A, column A, and column C. And so I'm getting something like 0.05. And if I want the standard deviation, I'm doing, well, this should be the expected value of r squared minus the mean squared. But that's the variance, and I need to take the square root to get from the variance to the standard deviation. So I'm going to do square root of that. Okay, now it's time for a question. So if you calculated summary statistics in class on Monday, and you calculated your standard deviation, you got 19.82%. We just calculated this as 19.7%. It's close, not exactly the same. Did I tell you something wrong? Are you worried? What's happening?
Is it the sample versus population?
Yes, exactly. So good. So Balaji, you said something about sample versus population thing.
Yeah.
Have you noticed that in standard deviation there's actually two functions? So let's try something. There's standard dev.s and there is standard dev.p. So if I do equals standard dev, and if I don't do anything, Excel defaults to standard dev.s. At least that's what mine does. So let me select the standard dev.s, and let me do standard dev.s on these sorted dividends. So standard dev.s, and my data is the sorted dividends. So this is probably what most of you did in class on Monday if you were getting a summary statistic of standard deviation for these points. And that's slightly different. So now let's try standard dev.p. Okay, so standard dev.p, here's these sorted dividends. And that's exactly the same. So what's the difference? So when I do standard dev.p, I'm telling Excel I have every possible value you could see. So I'm telling Excel that this column B is every possible value you could ever see for those market returns. And we actually had this discussion in class on Monday, right? We said, well, do you like the way I'm sampling? And we said, well, one objection is the way I'm sampling is I'm only letting the market returns see what you've seen, And that's fine for our game, but maybe if I'm really thinking about what 2017 returns are, that's a little limiting. Okay? So this standard deviation I've calculated here, it's correct for the game we played and the way I specified it. But more correctly, when we're thinking about the market and we're thinking about this data being a sample of what the market could do, right? This data doesn't have everything the market could possibly do in 2017. It's just a sample of things that have happened in the past. It's not every value that could occur. So standarddev.s says, you know, what I'm really doing is I'm looking at a sample of what could happen. I'm trying to summarize the standard deviation in this sample. And they're slightly different. The statisticians will tell you that this is doing something to eliminate what they call bias. I don't really want to get into that. What I want in your head is to understand there's two different standard deviation functions in Excel. And one of them, the .t, is telling that every single thing that could possibly happen you have in your data set. The standarddev.s is telling you this is just representative of what might happen. But it's not like these are the only possible values that can occur. Make sense?
So when we are analyzing, when we have taken a small sample from pool of data, then we should use the S, or otherwise, if we have the entire data and we're sure that this is the all possible outcome, then we use the pool.
Yes.
Is it?
And I would say there's a little bit of a philosophical thing you have to ask yourself when you're analyzing data, right? You have to ask yourself, does my data set contain everything that could possibly occur? Or is it actually just a small subset that I'm seeing? And I think most of the times it's a small subset, but of course it depends a little bit on application. And when we're specifying an exact distribution, the exact distribution is specifying every possible thing that can happen. So to some degree, when we're thinking of this as a CDF for the market returns, we're really thinking about this as an approximation. This isn't everything that can possibly happen, but this is an approximation of what. Okay, and then the last thing is, if we wanted to talk about coefficient of variation, we would do equals the standard deviation divided by the mean, and we would see that's actually pretty high. It's 1.7. In the die example, it was like 0.5, and I usually think of 1 as some kind of cutoff. Like, if you get a coefficient of variation above 1, that's pretty noisy, pretty spread out data. If you get a standard deviation less, a coefficient of variation less than 1, it's a little bit less variability, okay? And you could see that in the data set, right? The returns were really all over the place compared to what the average was. And that's exactly what this is saying. The returns were all over the place compared to what the average is. You got a high coefficient of variation.
Can we use the VLOOKUP function for the median?
Yeah, yes, that would be fine. I wanted to look it up manually because I wanted to make the point that actually there's a whole group of numbers that could be the median. And I wanted to make the point between what the Excel's median function was doing versus what this was doing.
Like how would we do that? I'm not sure.
So instead of answering this in real time, because I want to do the exercise, if you look at the spreadsheet I posted for the web server example, you would do it exactly like the VLOOKUP command in the web server example, except you would be using the sorted dividends, the PMF, and the CDF here. You're looking up a 50%. You're looking up what value of X corresponds to 50%. So you want these three as your table, and your lookup value for X is the 50% on the CDF. Okay, so the reason so the last thing I have for us is another exercise, and so I posted this in-class exercise on pension liability, and I think I remember from last time that there were a few actuary backgrounds in the class. Anyway, so it's you. Okay. Okay, well, you can tell me whether how happy you are with these tables, but you can think of yourself as an insurance company, and you're trying to figure out payouts for people based on how long they're going to live. And this is an example taken from our book. It's example 2.9, and I posted it on Blackboard. So can you all see it? Okay, so what I want to do is give you about 10 minutes to do it, and then we'll talk about it.
Really hot. That's a pretty good deal.
Oh, wait, okay, let me just, I might as well try now. I've got the, let's see. Oh, okay. And now I got a little icon now. She's like, just saying data station. Oh, yes, so good.
It's actually easier if you put the returns on the other side of the CDF. And so now, I know we have about 0.5. It always defaults to the first column. So I'm going to look up on the first column there, which is the CDF. And it's looking for where does it find, there's 0.5, and then it's telling me that 2.52%. So it's just easier to like copy paste and have those on the other side. Does that answer the question, or do you want to copy the formulas?
Yeah,
Okay.
That's what I got out of these numbers. Oh, absolutely. You mean kill people, get money. You don't have people to do that. You don't mind. It would be. It would be well done. It's like you and I, if we do these calculations, also do this program back. It would be perfect. Except in the total fact. Oh, that's excellent. You would have to do it one by one. Yeah. So.
Yeah, or I mean, I just got it.
No, okay. Changes. Question. Company. So I read this. So the question is, What's the probability that it will pay this pension for at least 2 years? Okay. So using her notes from last class, you would go to that formula and using to gather some expected probability of that.
Okay, so I have, my radar screen is, a lot of people have gotten 1 and 2, so I kind of want to put us all on the same page, and then you can move on to 3 and 4. So let me first just say, between the information you're given and the probability mass function in the CDF, what's happening? The information in terms of the way you were given it is you're sort of given the reverse of the CDF, but you know, that doesn't matter if you want to get to the probability mass function, which helps you. Here, whoops, this lowest value here is 0.173, so it's the probability I get a value greater than or equal to 90. And I've listed this as 94.4 because it says just pretend that somebody dies greater than 90 is 94.4. And what about this probability that I die at 87.5? Well, that should be the probability I die at 87.5 plus the probability I die at 94.4. So I'm just subtracting. So 0.333 minus 0.173. So I'm doing these subtractions to get from this, which is kind of the reverse of the CDF, to these probabilities. And if I want to give myself a distribution function, I can go back and I can add. In terms of answering the questions, did I have to do all that to answer question 1? No, not really. Question number 1 asked me, what's the probability I die after 80? And well, it actually told me right here, what's the probability I die after 80? It's 0.505. So I could have just read that directly from the table. And what about 2? It says the company's payouts will be at least $1 million. Well, for that one, I found, actually, I do find it a little bit more convenient to think about it in terms of the probability mass function. So at least $1 million. I'm paying out $40,000 a year, so $1 million divided by 40,000, I got to live for 25 more years. So that means I got to live to age 90. And age 90, it gave me this probability of 0.173. Okay, so that's 1 and 2. I think for 3 and 4, you might find it a little bit easier using the mass function, but you can see. Okay, so all on the same page there? No. Oh, okay, so no. What is it? Is it how I got the mass function or the distribution function? So actually, maybe I'll finish going over the example because I think we're getting a little bit close to the end. So help me with what is confusing on this page, because if there's something confusing on this page, the next one is 3 and 4 get a little bit, would be difficult.
I guess I don't action going on in the,
Ah.
or in the corner.
Okay, so okay, so this is the most important one to understand. So if you understand this one, we're in good shape. Okay, so what's happening? You're given the probability that you reach an age greater than 90 is 0.173. And I'm told that the only values, we're making some approximations, the only values that can happen are you're going to die at 94.4, 87.5, 82.5, 77.5, or these guys. Is those two statements okay? So these are there's this approximation, these are the only values that I'm going to die. Okay, so here it's telling me the probability of reaching greater than age 90 is 0.173. So the only value I here have greater than age 90 is 0.173. Here, so let's think about this one. 0.33, this is telling me the probability that I reach an age greater than 85, right, is 0.333. And you told me you're perfectly happy with probabilities adding. Okay, so probabilities add. So how do I reach something greater than 85? Well, I either reach 87.5 or I reach 94.4. Maybe this should zoom a little bit. Right? So 0.333, this has to be the sum of 0.173, which is the probability I reach 90, plus the probability I reach the 87.5. Okay, so if I subtract 0.33 minus 0.173, I'm getting exactly the probability that I reach this age 87.5. Okay, so I see a couple people nodding. So is that good? Okay, and so that same logic applies when I go to the probability I reach age 80. I can think of the probability that I last for longer than 80 as the probability that I last to 82.5 plus the probability that I last longer than 85. Okay, so I've got 0.505, that's the probability I get to 80. And here, 0.333, that's the probability I got to more than 85. So if I want this one, I just subtract 0.505 minus 0.333. So that's got to be the probability I get to exactly 82.5.
Okay.
So when you made your CDF for the web server example, that capacity, this is exactly what you did to go back and forth between that mass function and the CDF, right? The only difference here is I'm giving it to you in a slightly different form. I've given you sort of the reverse of the CDF. The values are decreasing instead of increasing. But the principle here is actually exactly the same. So what's important is that, do you see these values?
Yes.
Okay, so let me go just 1 minute over so that you get the last bit. The last bit is we know when you're going to die, or we know the probability you're going to die at different ages. And I need to translate when I'm going to die to how much money the company has to pay out. So here, oops, wrong one. Here, if I die at 67.5, how much money does the company have to pay out? It has to pay 40K per year, and it's doing that for 2.5 years. If I die at 72.5, the company has to pay out 40 per year, and it's doing that for 7.5 years. So here, all I'm doing, these are the ages I die. This is the function of the age I die. The function of the age I die is how much money the company is paying out. I want the expectation, the mean, the average money the company has to pay out. So this is my weighted average. So here what I'm doing, if you're doing it in Excel, you're doing a sum product of this Z column and the probability column. And if you want the standard deviation, you're going to square the Z's, you're going to do a sum product of the square of the Z's and the probabilities, and then you can use this little formula to get to your standard deviation. I'm posting these slides, so you don't have to worry about it. Films, I'm posting them after class. And if this went a little bit fast, I can start Wednesday's class doing this again. If if this was,
Please do.
is that a good idea?
Please do that.
Okay, okay,
Please
so
do.
sorry, I mismanaged a little bit how much time we need. But I will see you, so there's actually two things. We have a case next Wednesday. This is your first case. I absolutely encourage discussion. But make sure that the individual assignment is your own. So I do expect an individual assignment turned in, but definitely feel free to discuss with your neighbors. And what am I expecting you to get out of this class? I really want you to understand this relationship between the CDF and the PMF. So this stuff you were doing in Excel of subtracting to get between the probabilities and the cumulative frequencies, that's important. And these summary statistics, knowing expectation and variance, that's important. Okay, so those are like your takeaways. Have a very good long weekend.
Yes.
And as always, Wednesday, I won't see you.
Thanks, Ann, again.